All right, welcome back, everyone. In this lecture, we're going to look at the behavior of bosons in the in the quantum limit. In particular, we're going to look at the behavior of electromagnetic radiation and use that as our example of boson behavior, and see a little bit about how those sorts of calculations work. And in particular, we're also going to look at, or we're going to derive some of the most fundamental relationships or about light, and in particular about the light emitted from sources at thermal equilibrium. So to start with, we're going to think about light enclosed, electromagnetic radiation enclosed in a container which is everywhere at thermal equilibrium. So you can imagine being in a perfect idealized oven where all of the pieces of that container are at the same temperature. So we have essentially, again, a three-dimensional box in which our electromagnetic radiation is trapped, and therefore the electromagnetic radiation has to consist of standing waves of various frequencies inside this three-dimensional box. And so we've got another sort of a particle in a box kind of situation, except that we're talking about electromagnetic waves in a box. And we can think of each one of these modes of oscillation, each one of these standing waves, as a harmonic oscillator, because the electromagnetic wave equation that you can derive from Maxwell's equations gives you the same simple harmonic oscillator differential equation, and therefore the solutions of this are completely analogous to the simple harmonic oscillator mechanical oscillator solutions. And each one of these oscillators has a frequency associated with it, which is the speed of light divided by the wavelength. Each mode has two degrees of freedom, and so the Equipartition Theorem tells us that each mode contains energy of 2 times 1/2 kT. And while there is a limit on the lower frequency or the lower wavelength, the longest wavelength that this box could allow, and still have a standing wave where half the wavelength is the side of the box, there is no upper limit on how many waves in principle you could string across one side of the box. So each one of these standing waves has an energy kT associated with it. They're bounded on the bottom by the lowest frequencies that you could get a standing wave in this box of, but there aren't any limits on the upper frequency side, on the smaller wavelength side. And so effectively there are an infinite number of modes of electromagnetic radiation that you could stick in this box, and therefore if each of those modes has an energy kT associated with it, then there would be an infinite amount of radiation in the box, that the box would have a runaway infinite amount of radiation. We call this computational disaster the ultraviolet catastrophe. Now, obviously, this doesn't happen in real life because you don't open the door to your oven and there's an infinite amount of energy in there. So the question becomes, why does the electromagnetic radiation at thermal equilibrium not have an infinite amount of energy associated with it. And indeed, this turned out to be one of the earliest clues to the quantized nature of the universe. The gentleman who figured out what was going on, or figured out a way to solve the mystery of the so-called ultraviolet catastrophe, was Max Planck. And Planck's hypothesis was that electromagnetic energy has to come in discrete chunks whose energy is h, some constant, Planck's constant, times their frequency. And so as the wavelengths of the modes get shorter and shorter, as the frequency of those modes goes to infinity, then these HF chunks of energy associated with those modes get very, very, very large indeed. And because those chunks, because you can't excite a mode a little bit at a time, you have to excite it all at once. If that minimum energy HF isn't there in the thermal environment to excite that mode, then that mode won't get excited. And so doing this, and we'll work through the thermodynamics of that in just a moment, if you make this assumption that the energy comes quantized in chunks which are proportional to the frequency of the light waves, the frequency of the electromagnetic waves, then you can correct this ultraviolet catastrophe, and indeed you do predict precisely what we see in the context of electromagnetic radiation at thermal equilibrium. So effectively what Planck had done was invented the quantum harmonic oscillator as opposed to a classical harmonic oscillator. And in the quantum harmonic oscillator, we have energy levels are spaced at constant steps, so that each oscillator has an energy 0 or HF or 2HF or 3HF and so on. And so it's pretty straightforward to make the partition function for this system. You just go, well, that's 1 for the 0 term plus e to the minus beta hf for the first term, and e to the minus beta hf 2 beta hf for the second term, and e to the minus 3 beta hf for the third term, and so on and so forth. If we let x equal e to the minus beta hf, then this series is just 1 plus x squared plus x cubed, which has the solution, if you let it go to infinity, of 1 over 1 minus x. And so our partition function then is just 1 over 1 minus e to the minus beta hf. So that's our partition function. Once we have our partition function, we can calculate the average energy in our system. Our average energy then is just minus 1 over the partition function times the derivative of the partition function with respect to beta. So this is, well, minus 1 over our partition function. That's going to be minus 1 minus e to the minus beta hf. And the derivative of this with respect to beta, well, this is 1 over 1 minus e to the beta minus beta hf. So we're going to get a this thing to the minus 1, so that minus 1 is going to come down, and we're going to get that thing e to the minus beta hf to the minus 2 power, and then when we take the derivative of the inside, we get, well, the first term doesn't give us anything, but the derivative of minus e to the minus beta hf is just going to give us, the two minuses cancel again, and that's just going to give us hf. And so expanding all this out, that's going to give us, well, the minus is going to cancel with the minus 1. So that'll give us a, and then this is going to cancel with one of those. Oops, minus a hf e to the minus beta hf. Forgot the to repeat the exponential term there. So this is just going to give us hf e to the minus beta hf divided by the one remaining 1 minus e to the minus beta hf. And if we multiply that, do our usual trick of multiplying by the opposite here. So e to the beta hf on the top and e to the beta hf on the bottom. That's going to cancel with that, and this is going to turn into hf over e to the beta hf minus 1. So that's our average energy. And let's go ahead and get rid of the beta and put this back in terms of kT. So this is Planck's constant times the frequency over e to the hf over kT minus 1. So that's the average energy of our particles. And if energy comes in chunks of hf, then we could interpret this as saying that the number of excitations of each mode then is just given by the distribution function 1 over e to the hf over kT minus 1, which we call the Planck distribution. In terms of what this means for the ultraviolet catastrophe, we can see here that as we would go to higher and higher energies, right, as we go to higher and higher frequencies, then the energy associated with that mode, the single quantized energy associated with that mode gets very, very large, and thus the population of that mode, the number of energy chunks in that mode will be exponentially damped, right? So it's like those Gibbs factors. When HF gets much, much larger than the thermal energy KT, then these modes are exponentially suppressed, and so we don't have an ultraviolet runaway. We just have a finite amount of energy locked in the electromagnetic field. These units of energy, these chunks of energy HF, we nowadays associate those with the particle, which is associated with the quantized electromagnetic field, the photon. And these photons are spin 1 particles, so they have integer spin and therefore are boson particles. And indeed, we can see that the Planck distribution looks rather similar to the Bose-Einstein distribution, which, if we recall, e to the minus energy of a state minus the chemical potential of that state over kT minus 1. And indeed, if we want to reconcile the Planck distribution with the Bose-Einstein distribution, all we have to say is that this equals the Planck distribution if the chemical potential associated with photons is 0. Does this match our experience of photons? Well, in fact, it does. Consider, for instance, a very common reaction that we see in physics, which is that an electron either emits a photon, or vice versa, a photon collides into an electron and is absorbed by that. So we have a change of the energy state of the electron. It gets accelerated or decelerated by the photon, but a charged particle interacting with the electromagnetic field, that is indeed something we see happening all the time. And that if we looked at the chemical potential associated with this reaction, remember that we would then in equilibrium have to say that we just write down the chemical potentials on both sides as if this was an equal. So the chemical potential of the electron equals the chemical potential of the electron plus the chemical potential of the gamma ray particle at equilibrium. And the only way that that could possibly ever be true is if the gamma ray particle, if the photon itself doesn't have a chemical potential. This, from a relativistic standpoint, would just be the statement that photons have no mc squared rest mass energy, which is also something that is entirely consistent with our understanding of the electromagnetic particle photons. All right, so this tells us, this distribution here tells us then how many photons occupy each of the various modes, each of the various harmonic modes in our hot oven, in our hot cavity. If we want to calculate things like the total number of photons in our oven or the total thermal energy in our oven, then we would just need to sum these quantities over all of the allowed, or all of the modes, right? So the modes in our box, the allowed modes, are quantized so that the wavelengths are these half-integer wavelengths, 2L over n, or that the momentum associated with these photons is hn over 2L. Since these are ultra-relativistic photons, the energy, or particles, the energies associated with these photons are just the momentum times c. So that is hcn over 2L, where again our n can be n equals 1, n equals 2, n equals 3, n equals 4, and so on. We could associate more typical waves with these by saying the frequency of our wave is the speed of light over the wavelength. The energy is hc over lambda, which is again hcn over 2L. These are the allowed energy modes for our system, right? So this would all be for one dimension. Since we have 3 dimensions, we'll again assume a cubical box. Then our energy becomes c, but the momentum becomes a 3-dimensional momentum. So px squared plus py squared plus pz squared, take the square root of that, that's the magnitude of our momentum, and equals hc over 2L. We can convert those momenta into numbers for each mode, so nx squared plus ny squared plus nz squared, square root of that, and that has to again equal HCN over 2L. And so if, for instance, we wanted to calculate the thermal energy, well, again, there's two states, two polarizations, equivalently two spins for each mode. With EM radiation, we usually think of these as polarizations, and then we would sum over all the NX, NYs, and NZs, the energy times the Planck distribution. At that energy. So in other words, the number of photons occupying a particular mode of NX, NY, and NZ times the energy of that mode, sum over all of the possible modes, where the n's can be 1, 2, 3, 4, 5, 6, etc. Assuming that our box is not extremely small, then it's pretty straightforward to convert this this discrete sum into integrals. First, let me just note that this is going to be, again, we have this HCN over 2L over there, so we could write this as the energy here is HCN over 2L. So if we plug that in over here, that's going to be 2 times all those sums, NX, NY, NZ, times HCN over L, 2L, the 2's cancel. So that's the energy times the Planck distribution, 1 over e to the hf over kt minus 1. And then converting those triple sums to triple integrals, and doing the same adoption of a spherical geometry that we did when we did those same sums a lecture or two ago for the Maxwell distribution. Then we're going to get our integral here from 0 to infinity of dn, our radial coordinate in our three-dimensional n space, times the integral from 0 to pi over 2 of d theta, and the integral from 0 to pi over 2 d phi, n squared sine theta. So here again is just the volume element in spherical geometry, and we're integrating over that positive 1/8 of a sphere in n space, just like we did for the Maxwell distribution particle in a box calculation. This is a particle in a box calculation. It's just that our particles are bosons instead of fermions this time, and they're photons instead of electrons, but effectively the same integral being done here. And then we have the energy term, HCN over L, and the Planck distribution, E to the energy HCN over 2L KT minus 1. This is a little bit awkward to write down there, the HCN over 2L KT. So let's write energy equals HCN over 2L. And let's do a change of variables here. Instead of integrating over n's, we're going to integrate over mode energies. So that this means that 2L times the mode energy divided by HC is our number. Occupation area is our mode number, and if we take the derivative of that, 2L over HC times dE is our dN, and so we can rewrite this integral. Let's see, we'll put the angular stuff out front. 0 to pi over 2 of, let's do the theta integral. So sine theta d theta. And the integral from 0 to pi over 2 of d phi. And that's just going to give us, whoops, pi over 2, those two integrals. And then our radial integral, in this case our energy integral, 0 to infinity. What's left? The HCNs over L's, and 1 over e to the HCN over 2LKT minus 1. So this is just getting rid of that angular integral. And now we can accomplish this change of variables. So our energy is the pi over 2 from those angular integrals. And we can go ahead and pull out the HC over L. Pull that out front. The integral from 0 to infinity of n, which is 2LE over HC. And we had an n times an n squared. Oops, we lost our n squared in the previous. Yeah, it should have been an n cubed. You had the n here and the n squared there. So that gives us an n cubed. So this is our n cubed. And 1 over e to the mode energy over kT minus 1. And our dN turns into a 2L over HC d energy. And let's see, the 2 cancels with the 2. The HC cancels with the HC. The L cancels with the L. And so our energy integral, 0 to infinity, 8 pi L cubed, energy cubed, over HC cubed, and the integral dE over E to the energy over kT minus 1. L cubed is volume. So if we divide both sides of this by volume, that'll be energy per unit volume, or in other words, energy density. So we could call that little u energy density. And this is the integral of 8 pi energy cubed over HC cubed e to the energy over kT minus 1 d energy. So this is our energy density is some integral over mode energies of this quantity. Or in other words, we could call this quantity the specific frequency or the energy specific energy density, the spectrum essentially. Energy density as a function of E, such that the total energy density is this energy density as a function of E times dE integrated over all energies. All right, so this is the relative amount of energy stuffed into each energy bin if you wanted to plot versus energy, the amount of energy coming out at any particular any particular energy HF essentially associated with. So you could think of this as the energy per frequency or the energy per wavelength, or in this case it's the energy per energy. It's a relatively simple conversion to convert per energy to per hertz, or to per centimeter for wavelength or something like that. So this quantity in here is essentially the spectrum. What we can say here is that the spectrum as a function of energy is 8 pi over hc cubed energy cubed e to the energy over kt to the minus 1. This is the Planck energy spectrum, or the Planck spectrum in energy units. Anybody who's a spectroscopist is familiar with this. Astronomers use this all the time, or spectroscopists of all sorts, often converting from energy units into either frequency units or wavelength units, but essentially the same spectrum. We can note that this behavior has a maximum, and which is right here, and we can compute that maximum. Before we do so, let's make this thing a little bit easier to deal with. Do another unit conversion, or another coordinate transformation here. In this case, we're going to let x equal energy over kt, our pretty standard coordinate transformation at this point, so that the energy could be written down as xkt, and our dE then could be written down as kt times dx, and therefore our energy density U over V is going to be 8 pi over hc cubed times the integral from 0 to infinity of xkt cubed times kt dx over e to the x minus 1. And if we pull out all the extraneous factors of kt, this is going to be 8 pi, 3 factors of kt from the x cubed, or from the energy cubed, and another factor of kt from the dE term gives us 4 factors of kt out front. And 3 factors of hc on the bottom still. And now our much simpler integral 0 to infinity of x cubed e to the x minus 1 dx. Again, there you can go look in Appendix B. There's a nice solution for this. or you can go look it up, or you can plug it into a numerical integrator. In any case, what you get out of this is the unlikely quantity pi to the 4th times 15, or divided by 15. And so therefore our energy density is 8 pi to the 5th kT to the 4th power over 15 times hc cubed. That is quite a bundle of constants in there. The working thing to take away from this is that energy density is proportional to temperature to the 4th power. So that if you double the temperature, then you have 16 times the energy density. That's a very, very sharp power law. This integrand here, x cubed over e to the x minus 1, it's pretty simple. Just take the derivative of this, set it equal to 0 to show that the energy of peak of that spectral peak happens at x equals 2.82. So that in other words, the peak in the energy spectrum happens at 2.82 kT, a result called Wien's law, and there are equivalent versions of that for the peak wavelength and the peak of the wavelength the energy spectrum versus wavelength, and the peak of the energy spectrum versus frequency. As the temperature goes up, the energy of this peak goes up. Indeed, it will shift out to higher and higher energies as the temperature increases, like so. Which makes a certain amount of sense. The hotter your system is, the more of these higher energy modes of the electromagnetic field will be excited in thermal equilibrium for that system. Having calculated the energy density, we can also do things like calculate the heat capacity, which is du dt, holding volume constant, which is just 4a t cubed, where a is 8 pi to the 5th k to the 4th times our volume over 15 hc cubed. The reason the 4 wasn't folded in there is that basically that 4 comes from the t to the 4th getting having its derivative taken. So the 4 came out of the derivative. This a factor all comes out of this. This will be true at all temperatures, right? Because this was not an approximate result. This was basically an exact result, and is true all the way down to temperature equals 0. And so we can find the entropy for our electromagnetic field just by integrating our heat capacity from 0 to whatever temperature we're looking at. dt, integrate our heat capacity and temperature, and that's 4 times a times the integral from 0 to t of t prime squared, because we took the t cubed and divided by t, so we just got t squared. And the entropy then, as a function of temperature, is 4/3 a t cubed, or 32 times pi to the 5th over 4 45 times the volume of our electromagnetic field that our electromagnetic field is sitting in times kT over hc cubed, and this extra factor of k sitting at the end. This will also, if you went through and derived a similar relationship for if we went through and derived a similar relationship for the number of particles, then we would find that the entropy is also proportional to the number of photons at a particular temperature. So one application of this would be, I mean, this is a description of the electromagnetic field anytime that electromagnetic field is in thermal equilibrium with its environment. And so, for instance, it would describe the electromagnetic field inside a hot sealed box or inside any closed system at thermal equilibrium. The most obvious or extreme version of an application of this would be the thermal cosmic microwave background, the relic energy, or the relic light from the early universe when the universe was in a hot opaque setting and therefore had a thermal equilibrium associated with it. The photons in the universe were in thermal equilibrium with the environment of the universe, and there was a black body spectrum, a Planck spectrum here of roughly not quite 3,000 Kelvin or so, and then about 13 billion years ago or so, give or take, a few 100,000 years after the Big Bang, though the universe became transparent, those photons ceased to exchange energy with their environment and have just been streaming freely through space ever since then. Now, the universe expanded, and as part of that expansion, the rate of ticking clocks in the universe is different now than it was when the universe was much smaller, and so that 3,000 Kelvin black body, that 3,000 Kelvin Planck spectrum, is now a Planck spectrum with a temperature of about 2.7 Kelvin. But that cosmic microwave background radiation was still discovered famously by Penzias and Wilson by accident, and then later by many other astronomers who have been using it and measurements of it to infer things about our universe ever since. So the Planck spectrum describes radiation, describes the radiation field, the electromagnetic radiation field inside our hot object, inside our oven. But what about outside of our hot object? How does this radiation then interact with the rest of the universe? And so we could imagine taking our box, taking our oven, and putting a small hole in it, allowing a window through which our radiation can pass. We could let this window have some area A, and since all of the light, all of the photons in this box move at the speed of light, then if we want to imagine all of the stuff that's going to come through some window here, then just before that, all of the photons that were going to come through that window were in some sort of a circular arc over here, and so we could imagine some little chunk over here at an angle theta from the normal to our window, and the volume of this little chunk is going to be r times d theta. So that would be r d theta. That's this length times an r sine theta d phi, the usual again angular volume element, times a thickness here, which is the speed of light times some little time dt. That's how thick this sort of spherical shell here is, c times dt. We know that the energy density, u over v, in our box in the electromagnetic field is 8 pi to the 5th over 15 times kt to the 4th over hc cubed. And therefore, the volume times the energy density would tell us how much energy is in that spherical shell, which is all going to go streaming out the window. All right, so the energy density in our chunk then would be so the energy density in our chunk here is going to be u over v, our energy density times c dt times r squared sine theta d theta d phi. And the probability of, so that's how much energy is out here, but those photons are going in all sorts of directions, right? And only a small piece of all directions goes through our area. And so the probability of escape is basically the solid angle subtended by this area. Basically, how big a cross section does that area measure versus all of the possible directions the light could go? Well, there's that then is just equal to, well, the size of that area goes as 1 over r squared. So that's area over r squared. And there's a cosine theta term, which is basically the area times cross section, or cosine theta is the cross-sectional area. Goes down as r squared, and there are 4 pi steradians. That's two-dimensional radians. 4 pi steradians that you could go through in all directions. So a cosine theta over r squared, that's the piece of a sphere that is the piece of all directions that goes through our window, and 4 pi is all directions. So the probability of escape is just the relative size of our window versus the whole sky, basically, as far as the photons are concerned. And so we take this, we multiply it by the energy in our spherical shell here, and that gives us the energy escaping, or in other words, the energy going out through our window. That's A times cosine theta over 4 pi times the energy density times c dt sine theta d theta d phi. And now if we want to do the total energy, we have to integrate over those angular distributions. So the total energy escaping each second that's going to be the integral from 0 to 2 pi d phi, and the integral from 0 to pi over 2 d theta. So theta can only go from halfway, we're going to basically integrate a hemisphere here. Times, again, a cosine theta over 4 pi u over v c dt sine theta. And we'll pull a bunch of constants out front, so that's 2 pi from the integral times the area over 4 pi from our probability. The energy density U over V comes out, C dt comes out, and we've got the integral from 0 to pi over 2 of sine theta cosine theta d theta. This is going to give us a result of 1/2. And so the total energy escaping then is A, the 1/2 cancels with the 2, the A over 4 U over V C dt. And so that's the energy in some time dt. Let's convert that to a power per unit area, right? So the bigger the window, obviously, the more power is coming out. So the power per unit area then is just C over 4 U over V, which is 2 times pi to the 5th power over 15 times kt to the 4th power over h cubed c squared, because the c canceled with one of the c's, and that is what we call the Stefan Boltzmann constant, sigma times t to the 4th, where sigma equals 2 pi to the 5th k to the 4th over 15 h cubed c squared, which is 5.67 times 10 to the minus 8, one of the most awesome physical constants you're ever going to find in physics. 5, 6, 7, 8. It's great. Watts per meter squared Kelvin to the 4th. This is a crazy set of units. Nobody ever remembers this. What we remember is power is sigma t to the power per unit area is sigma t to the 4th. That's really easy to remember. You go up, look up sigma, or even remember 5, 6, 7, 8, and there you go. This is the Stefan Boltzmann constant. Almost, I've never seen it as anything other than sigma. All right, that's the power per unit area coming out of any system which is in thermal equilibrium. So the power streaming out of a thermal equilibrium oven or something like that. But in fact, this result is even more general. It turns out to be true for any perfect absorber or any perfect emitter. So any black body So this is often called blackbody radiation. I even used that term reflexively earlier in the lecture because blackbody radiation is one of the standard assumptions of most astrophysical sources, at least is one of the standards to which we compare things. So blackbody radiation is a very general result, and it's for any essentially close to perfect absorber. So if you're not reflecting much back into the universe, if most of what comes in gets absorbed, then imagine, for instance, that you stuck, here's our oven, and over here you had a perfect absorber, right? Well, the oven and the absorber can exchange photons with one another, right? And if they are at the same temperature, temperature here and temperature there, then this is an exchange of energy in the thermodynamics sense, and therefore if these two objects are at the same temperature, then an exchange of radiation between them should produce zero change in energy, because energy shouldn't flow between two objects of the same temperature. It's a slightly subtle argument. If this object is a perfect absorber, it's not reflecting any of the photons that come out of the oven, it's just absorbing them, then it must also emit exactly the same energy that it's absorbing from the oven if it's at the same temperature, because if it didn't, then that would violate the second law of thermodynamics, essentially, that temperature flows from hot to cold, or the energy only flows from hot to cold. Therefore, if no net energy must flow, then the total energy flowing into this must equal the total energy flowing out of that. In other words, the black body has to have exactly the same power as the oven. But it's even worse. We could stick some sort of a filter which only lets through a narrow frequency in wavelength, so that we could repeat this experiment basically frequency by frequency, or wavelength by wavelength, and still the same argument must hold. If this is at the same temperature as the oven, then there can't be a net exchange of energy. So it's not just that the bulk power must be exactly the same as from the oven, but it must be that the bulk, or the wavelength by wavelength, frequency by frequency, energy by energy spectrum must be exactly the same. In other words, that this spectrum that we derived back here, this spectrum not only holds true inside a hot oven in thermal equilibrium, but is the spectrum emitted by any perfect emitter at a temperature T. That this Planck spectrum is a general result, the general result from, or of, any emitter emitting perfectly. As a final example, let's look at the sun and Earth system. So the sun has a luminosity of something like 4 times 10 to the 26, 3.9 10 to the 26 watts, which we receive here at Earth as a flux of the sun of a little bit less than 1,400 watts per meter squared. So the integrated energy from our sun is per square meter landing on the surface, or at the top of the atmosphere, it's about 1,370 watts for each square centimeter. Now the radius of the sun is approximately 100 times the radius of the Earth, which is about 7 times 10 to the 8th meters, which gives us a surface area for the sun of about 6 times 10 to the 18 square meters. And so if you take our power per unit area, sigma t to the 4th, right, multiply it by the surface area of the sun, then the luminosity of the sun is this power per unit area, sigma T to the fourth, times the area of the sun. And if we solve that for the temperature, L sun over sigma times the area of the sun to the fourth power, we find that the sun that produces 1,370 watts per square meter here at the Earth has a surface temperature of something like 5,800 Kelvin. Technically, that's not the precise temperature of the gas at the surface of the sun, but it's pretty close to it. Actually, the sun is pretty close to a black body emitter. We would call this the effective temperature, technically, of the surface of the sun. And this has a peak in the energy spectrum, which corresponds to about 1.4 eV, or about 900 nanometers, or 0.9 microns in the near-infrared spectrum. So the maximum amount of energy coming out of the sun peaks just beyond the reddest thing that our eyes can see. Now, if we think about the sun as an object over here, and the Earth is an object over there, then some fraction of the sun's light gets absorbed by the Earth. And so we could go, all right, well, how much energy does the Earth receive from the sun? Well, if that's going to be, we approximate this as the Earth is a circular cross-section, then we take the solar constant, multiply it by the cross-sectional area of the Earth, pi radius of the Earth squared, right? That's the energy in. That's the energy from the sun that's absorbed by the Earth if we make the Earth take the approximation that the Earth is a black body and is absorbing everything. Then that energy in must also, the Earth must also then have a finite temperature, and it would radiate that same energy, but it's going to radiate it from its entire surface. So that's going to come off the surface area, 4 pi radius of the Earth squared. So it only absorbs as a cross section, but it emits as the full sphere, sigma times the temperature of the Earth to the fourth power. Pi's cancel, the radiuses cancel, and what we're left with is that the temperature of the Earth then that we would expect to see out of this is going to be the solar constant divided by 4 sigma to the fourth power. And if we plug in our 1,370 watts per square meter, 4 times 5.67 times 10 to the minus 8 on the bottom, and go to the fourth power, what you get, 1,370 divided by 4 divided by 5.67 10 to the minus 8, and take the fourth root of that, you get 279 Kelvin. 279 Kelvin. So that's barely above freezing. That's an average temperature of the Earth. That's not too terrible an approximation. However, it turns out that we forgot a couple of things. First of all, the Earth's albedo, that's its reflectivity, is roughly 35%. So only about 65% of the solar flux, the solar constant, actually gets absorbed by the Earth. And so if we did that same calculation, but we lowered the flux by 65 or to 65%, so 0.65 times our 1370 watts per square meter over 4 times 5.67, 10 to the minus 8. Wow, it looks that's even better. 4 times 5, 6, 7. Yeah, all right. Anyway, I'll stop with that now. 1 over 4. Then you get about 250 Kelvin, which is super chilly. That is a little bit brisk for the surface temperature of the Earth. It is roughly the natural temperature the Earth would have if it didn't have an atmosphere. If the Earth had no atmosphere but 35% reflectivity as it does now, if you ripped the atmosphere off of the Earth, then it would cool down to about 250 Kelvin rather than 300 Kelvin. However, there's another effect that we've ignored, which is the light from the sun, which comes in from a 6,000 Kelvin black body, which peaks out in the near infrared, goes through the atmosphere fairly readily. The transmission of the atmosphere is pretty transparent at optical and near infrared wavelengths. However, at the more like 10, 20, 30 microns that this not quite 300 Kelvin black body of the Earth will peak at, the Earth's atmosphere is significantly more opaque, particularly carbon dioxide and water molecules tremendously absorb at mid and far infrared wavelengths. And so at the infrared wavelengths that the Earth wants to emit as a much cooler black body, the atmosphere is fairly opaque. Not completely, but not it absorbs quite a bit. And so your book does a very simple model of the greenhouse effect, which is what this is talking about, in the following way of thinking about things. So imagine a very simple model of the atmosphere as just a single layer, kind of like a thermal blanket above the Earth. The solar flux comes in, right? So we have F sun coming in, but some 35% of it gets reflected either off the clouds or off of ice on the surface of the Earth, etc. So only about 0.65 F sun gets absorbed by the Earth. For the atmosphere to be in equilibrium with this 0.65% of the solar flux going in, for the atmosphere to be at a constant temperature, then it must be in thermal equilibrium. So there must be, in fact, that same 0.65 F sun coming out of the atmosphere. And if it's radiating upward at 0.65 times the solar constant, it must also be radiating downward at 0.65 times the solar constant. And so there is an equilibrium here where the Earth radiates outward, and this would be sigma TE to the fourth. That's the rate at which the Earth is radiating, but that has to be in equilibrium with the 0.65 times the solar constant coming from the sun, plus the 0.65 times the solar constant reflected or absorbed out of the atmosphere. And so if you do that, Then our temperature calculation gives us that's 0.65, but we have two factors of it, one coming from the sun and one being absorbed and re-emitted by the Earth's atmosphere over 4 times 5.67 10 to the minus 8 on the bottom to the 1/4 power. And I kid you not, this comes out in this calculation as 298 Kelvin. It's not that exact. This is not that good a model. It's pretty funny that it comes out exactly as 20C. This is a very blunt version of the greenhouse effect. In reality, what we should really be doing here is doing both an integral over wavelength space of the transmission function, so that you get the wavelength dependent transmission function, and that this absorptions are dependent on the actual parts per million of the various species that are doing the absorbing. You also have to take into account that we don't have a single slab atmosphere, but in fact there's a variation of density, and so this absorption by the atmosphere is actually a much more complicated process. You would actually have to do a rate process, and we would have to do a fair bit of discussion of what we call radiation transport to actually properly calculate the propagation of the light through this atmosphere. Having said that, the basic concept is captured here correctly, even if only approximately numerically. The basic idea is that the Earth-Sun system is not in a thermal equilibrium, and indeed that the energy into, I mean, the Earth has to be in thermal equilibrium at some level, but the Earth and the Sun are not at the same temperature, so the energy coming in from the Sun comes in a different frequency space, a different part of the spectrum than the energy that tries to leave from the surface of the Earth. And therefore, the Earth's atmosphere is a lot more transparent to the incoming energy than it is to the outgoing energies, which is what raises our temperature from its sort of natural 250-ish Kelvin for this distance from the sun to the more like 300-ish Kelvin that we actually see on the surface of the Earth. And it's in those more complicated calculations that you would be able to detect what the effect of changing the amount of absorbers in the Earth's atmosphere, changing the transmission of the Earth's atmosphere by changing, for instance, the amount of carbon dioxide in the Earth's atmosphere, the amount of water vapor in the Earth's atmosphere, the amount of the other greenhouse gases, changing those abundances in the atmosphere changes essentially the balance of how much what this fraction has to be coming out, and the relationship of this energy coming out to the energy being released by the surface of the Earth, because there's a transport problem from the Earth through the atmosphere out into space. It's a more complicated problem than we've got the tools to deal with here. But the basic idea is still the same. It's more transparent coming in than it is going out. So the greenhouse effect is always going to raise the temperature of the Earth, which is a good thing because 250 Kelvin is an unpleasantly cold Earth. But it does depend on how much of these greenhouse gases are in the atmosphere. This stuff, by the way, is not even remotely controversial in terms of the physics. Indeed, it's all measurable directly. What's more controversial has to do with the notion of how much is the atmosphere of the Earth changing and so on, although at this point, frankly, that's not even really controversial to anybody who's taken a fairly serious look at the data without strong political bias at this point. But all right, enough of that. We're going to move on in the next lecture and talk about the Debye theory of solids, sort of a better version of thinking about solids than the Einstein solids. It actually has a fair bit in common with what we just talked about in the blackbody spectrum, so it's a good place to go from this point. Until next time.